thanks to SciShow, we got to see a natural fissile nuclear reactor. And remember, the three things you need would be an atom that can split apart pretty quickly and easily in that case, and in the case of a regular nuclear reactor, that atom that can split apart quickly and easily would be uranium-235. You need something to do the splitting. In this case, it's neutrons. The neutrons catalyze the reaction so that it begins. But you also need a way to control the reaction, and that way to control the action was water. So all three of these things occur in a regular nuclear reactor, except now controlled by humans instead of letting those kilowatts go to waste.
So how does a power plant work in general? Well, minus solar energy, all of the other wind, thermal, and nuclear and hydroelectric all work on the same principle. And that principle is turning kinetic energy into electricity using a generator. In the case of hydroelectric power plant, the water turns the turbine turns the generator produces electricity. In the case of a thermal power plant, coal, oil, or natural gas burn, and that's where the carbon comes from, heats the water water turns to steam, which turns the turbine, which turns the generator. Nuclear power does the exact same thing, but notice that instead of a fire here, which produces that carbon we were talking about, you have fissionable material in your reactor. The control rods move in and out of this reactor. The control rods move in and out to moderate that reactor. Notice it's filled with water. That water gets hot. The hot water goes over here. The water turns to steam. The steam turns to turbine, which turns the generator.
Now, an important thing here, and when you see this in the news, I want you to understand what it means. SciShow is talking about how there's a difference between two different types or isotopes of uranium. Uranium-235 is the type that can be used for nuclear fuel. It's good at making chain reactions, whereas the U-238 is much more abundant naturally, but it's not easily fissile. What we do is we take the natural uranium ore, we enrich it to be low enriched, so we can use for nuclear power plants. They mentioned the Oklo reaction was at about 3% concentrated U-235. Iran, because of the Iran nuclear deal, is limited to concentrating their uranium to 3.67%. And one of the reasons this is an issue, one of the reasons people are concerned about letting other countries use low enriched fuel, is that it doesn't take a huge amount of effort to go from your 4% uranium to 20% uranium. And it doesn't take a huge amount more effort to go from 4% U-235 to 90%, and 90% would be weapons grade. So when you hear about in the news the monitoring of centrifuges, that is what they're talking about. Centrifuges are used to take natural uranium ore, which only has a little tiny bit U-235 fissile material, and concentrating it by removing the 238 from the mix. So we monitor the centrifuges in order to make sure that people are staying within limits. They also went through in the SciShow video how this chain reaction works. In this case, a neutron strikes a U-235, and it temporarily, for a very, very brief period of time, microseconds or less, becomes U-236 in this little excited state. Well, then that U-236 has its catalyzed fission reaction. Because of the neutron collision, it splits in half into krypton and barium, releasing 3 neutrons. Let's see what that reaction looks like if we play it forward. You take your U-235, bombard it with a neutron, it becomes U-236 just for a moment, has its fission, but those 3 neutrons, what are they doing there? They're having a chain reaction, right? The chain reaction occurs because those 3 neutrons that were emitted in the first reaction, then go hit other fissile material, the U-235, and they also have a reaction, each emitting 3 extra neutrons that go hit the other 235. The U-238, when it absorbs a neutron, slows the reaction. So having a lot of 238 will prevent it from chain reacting. Compared to traditional fossil fuels, fission-based nuclear power has huge advantages. It's carbon-free. There's significant less cancer risk from a nuclear reactor. You might have noticed this from Friday as well and been a little bit surprised. If you're thinking to yourself, why is a nuclear power plant less likely to cause cancer? Well, that's because for the people living nearby, all of that reaction is cooled by water that's contained within the reactor. And unless something really catastrophic happens, which we'll talk about in a second, unless something really catastrophic happens, that nuclear radiation is highly studied and regulated. Whereas when you have a coal burning or a fossil fuel burning power plant, that releases a lot of smoke into the atmosphere, which statistically increases your lung cancer risk, in addition to things like coal mining accidents and groundwater disruption and all those other good things. Another very important point here is fission-based nuclear power has significantly higher energy density, meaning for every 1 kilogram of coal, you get about 1,000,000 times more energy out of the nuclear reaction versus the chemical reaction. And you know what, guys? We actually have a fission-based nuclear power plant right by us. This one picture right here, that is the Millstone Nuclear Power Plant in southern Connecticut. But there are cons. One problem with fission reactors is you get runaway reactions as a possible outcome. You saw that every 1 singular reaction produces 3 neutrons. So you could get a runaway reaction that would become more and more energetic until bad things. Other potential problems is that krypton and barium, the storage of waste after your uranium is used, is problematic. We're still trying to figure a way out of that, but I will talk about it later. And lastly, enriched U-235 could be weaponized. As I showed in the previous slide, it only takes a little bit of extra effort to go from having 4% enriched uranium to 20 to 90% enriched uranium. So that is one concern. To be fair here, for runaway reactions, an important thing to note is those are very, very rare and require very extreme circumstances. In the case of this picture right here, this is from the Fukushima Daiichi plant in 2010, and that only had a runaway reaction because a series of really extreme events occurred. First, an enormous earthquake, followed by a 50-foot tsunami. But even then, the backup power continued working for hours and hours and hours. However, what had happened was that the original electricity that's supposed to power the plant and keep that water coolant running through, that never came back online. And because it never came back online, the backup systems and everything worked as expected. But it couldn't cool the reaction fast enough. Remember, these are water-moderated reactions, and therefore it had a chain reaction. Now, I just got finished watching one of the best science shows I've watched in a long time, about Chernobyl. Chernobyl actually happened the day before that I was born. And you saw in that image right there with those pieces of metal that were awkwardly lifting up, each one of those is a 350 kilogram, so that's about a 700-pound control rod. And when those were moving up and down, that was because there was a huge overheating issue in the plant. That design has been retrofitted, so that should never happen again. And that was basically a series, like in Japan, of extremely unfortunate coincidences that led to this particular episode. That being said, go watch Chernobyl if you get a chance this summer. It is totally worth it. Absolutely excellent physics there. And so when we get back, What I'd like us to do is try out some questions on fission and fission reactors on your own, and then we'll talk about a different alternative that is coming up, hopefully, in the future.